Yeah, thanks a lot for having me here. So it's really a pleasure and honor. And as already introduced, I'm not deep into the sustainability domain, but I see many natural connections from my background, which is material science and computer science. So the background is actually that my institute is mainly doing material research, and it's actually in a very broad range of materials. You see on this picture, for example, nanoparticles, ceramics, glass, batteries, and coating. So this is our actual mission, and my personal motivation to rethink digitalization and fair data and sustainability aspects started in my PhD, because actually my PhD was very focused, of course, on material performance. So I did design elastomer composites with silicon and metal particles that were processed as layered structures in the lab, and were tested thoroughly and generated a lot of data, imagery, and was also connected with some electronic device to end up with a hybrid material electronic system that aims as a sensor skin for robots. So I was pretty happy with the results, but I have to admit I completely ignored any sustainability aspect. So I was just focused on the performance of the material, and I also was not really focused on making this result really shareable with others. So even if I put my data, my research outcomes to someone who can access the sustainability aspects, he had a really hard time dealing with this mess of data. So this is a motivation to make it better in the future. And vice versa, if you look at the big picture of governance and policy, there's clearly the agreement that we have broad societal challenges, the climate crisis, sustainable energy solutions. And in this way, of course, advanced material solution brought us solutions in the past, but also a lot of problems. And what we now have to admit that we can use, or we need to rethink and improve advanced materials to mitigate those challenges. So advanced materials could also be definitely the solution to get clean energy and to substitute critical raw materials in existing products. Yeah, it's a little bit slow to click all. Yeah, okay. And if you look at the European strategy, I mean, the Green Deal is really condensing this to a twin transition where you have the digital transformation enabling a green transition with advanced materials, which is also part of important movements like the Manifesto of Advanced Materials, and then now the Communication Advanced Materials for Industrial Leadership, and the now announced partnership, a founded partnership in innovative advanced materials and the Materials Commons ecosystem for materials research in Europe. So we really see the issues of the domain and the issue of society are reflected in an agenda, but of course we need to fill this agenda with actual solutions. And I will start with a concept that promises to improve the way we research materials and make it different from a conventional way. So the traditional approach is that someone is in the lab and gathering the data, and someone, maybe the same person, is analyzing the data. And so that's the conventional way to do it. And if you look at our demography, it's not like we can just multiply the effort and put more and more people on the same jobs. So just putting more humans on this problem does not improve anything, because we do not have the resources. Instead we need to rethink how we do gathering data in the lab. So we need to automate a lot of procedures to get the raw data, and we need to automate as well the way we analyze the data and evaluate the results in a digital world. And if you combine this automation on a lab level and automation on a data processing level, we can really close a loop of optimizing materials. This is the concept of what we call material acceleration platforms. So integrated platforms that really accelerate research on advanced materials by having this combination of highest throughput testing and big data and AI approaches to handle the data output of such high throughput approaches. And we expect that the costs and the time to market with this approach is significantly reduced comparing to traditional approaches. And one thing is that, of course, we can have this iteratively improvement of solutions by every executed loop. And also we can evaluate, we can have a multi-parametric optimization, which is difficult for humans, but much easier for machines. And for example, approaches like Bayesian optimization, they can really find an optimum among maybe a 10 or 20 parameter space. And of course, in this context today, those parameters are maybe reflecting both the technical performance and the sustainability of a solution. So we may find the best compromise in this, and we need to be very efficient on the way to find the best solution. So not a trial and error, but precisely selected plan of experiments that leads to the best outcome. This is also it's a kind of an agreement among large research institutes active in the domain, and we also reflect this in the, let's say, in the architecture of our digital transformation in our institute, that we need to connect the kind of the shop floor, the lab level of experiments, this automation, through an integrated information layer where human actors and machine actors can coexist, while we enable interoperability with data spaces, and in direction of industry like Catena-X for the automotive sector, and also academic approaches like the European level and on the German national level like the Platform Material Digital. And this is then where we can execute this loop of optimization locally and also in cooperation with other partners. And to bring it a little bit more into reality, here's it's a demonstrator of how to interact with lab experiments in the future. So this is a live demo we made remotely over from Switzerland to Germany, where we can select experimental setup in our lab, and we can send a recipe to the machine. We can have a live access to the equipment, and really can, for example, check if the setup is already configured correctly, and then we can schedule experiments without having to deal with the local setup. That means we can also share maybe expensive or complex experimental setups with other communities worldwide. And of course, the setup is then a blueprint for perfect data documentation and fair data documentation, collecting all the results in a structured way and maybe already publish them on a repository. And moreover, we can also not request single experiments from the setup, but also we specify maybe the target outcome of an experiment regarding this multi-parametric optimization. And then we schedule an optimization challenge for the setup, so it iterates over and over the experiment. In this example, it optimizes the color, so it's a very simple example. But we just can wait until the perfect result was achieved without dealing with the details, and can focus on the orchestration of such optimization. In order to connect this automation on the lab level, on the data handling level, with other domains, I would say the common conceptualization is key. So we often talk about the same things but use different vocabulary. That makes it hard to really connected domains. So I would say in most domains, processes are a key element of conceptualizing the world. This is true for us as material science, and it's definitely also true for life cycle assessment and sustainability assessment. And if it comes down to, if you really condense the process, is it something that transforms material or information, and it typically also uses energy or provides energy. And there are, of course, surrounding elements like tools that are needed as a participant or human actors. You can also make this build, of course, complex process out of elementary steps. But this is very fundamental, and thinking in this conceptualization helps us to identify that we often speaking about a common aspect of our world and our data. And one way to model data also in an interoperable way is to look at existing broader standards. So instead of setting up a new data schema, a new exchange format, we should look at what is already there for conceptualizing our concepts. And what we identified is that the JSON family is a well-established way to express machine-readable data, and there's an extension to it, which is a JSON schema language, which provides validation, but also you can get APIs from it, you can generate code from it, you can generate human interfaces from it. So you get a lot of tooling, but just by using an established language to express the shape of data. And on the other hand, in our domain, a lot of people talk about ontologies and vocabularies to make data really interoperable. And there's also JSON-LD, which exactly provides this mapping of a syntactical expression of data to a semantical and interoperable way of data by translating it to RDF. But it's not like we need to reinvent a way to generate this ontologized graph data, but we can stick to well-known tools and combine them to something that we can work with. So we have this standard family to generate interfaces to data, but also to generate this RGF representation of everything we store. Okay, maybe jump over this. This is really technical. And even if we look at the taxonomies already established, they're quite broad. So on some levels we have, for example, if we look at quantities and units, so everybody needs quantities and units, but there are many existing vocabularies expressing the same meaning if it comes to what is a length, what is an energy, and what are units for this. So just some examples. We have ontologies like MO and QDT, ontologies from this digitalization efforts, but also in the industry scope. We see redefinition of such fundamental aspects, and also in the LCA software, you find an inventory of quantities and units. So everybody is replicating the same conceptualization of basic material characteristics or physical characteristics. And what we see here that we should talk about a common inventory of such things in a already applicable way using this existing schema languages to define a schema for using this physical quantities and expressing our data. So the interoperability is really built in without any further mapping needed. And by using these approaches I have shown before, we can use not only a repository of interoperable concepts, but also generate both a code perspective and a visual perspective on this. So we have people that are using this programmatically, and people who need a UI interface to maintain data, to validate data, and so on. Yeah, and use cases where we use this, if you have this inventory of templates that represent a certain part of the data, you can really yeah, of course, we can represent arbitrary elements. So, for example, we had a project where we collect raw data, raw material information. So we connected of location information with physical properties of the brine source in this case, and chemical components in the brine in a graph that, yeah, connects this information in a linked data graph. But we can also extend this to manufacturing. So this is an example where we have lab scale battery cell manufacturing, and where every cluster here of data represents a single processing step in the value chain. So we go from separation of electrodes over drying and stacking, filling, formation, end of line tests. So every process pattern contributes one piece of data to the overall value chain, and having this all machine readable in a connected graph allows programmatic access, or also AI optimization access to this data. Yeah, just to give some examples. Example, here we see all the measurements on every single component in the process, and here we see the parameterization of the drying procedure, temperature, humidity, and this, images of the stacking and parameterization of the formation and so on. So it's all the information you may need to make optimization of the product from a technical perspective, but also the information you need to optimize the sustainability or to calculate energy consumption or resource consumption on the final product. Yeah, and if we look at what data spaces should form in the future regarding data exchange in the industry, this graph of information may be then separated between different institutions, and they exchange the information then based on a digital contract. But it's very important that there's no further agreement needed on what is shared, but we have this common conceptualization of a process and can then optimize our own product, for example, based on the data we get from our suppliers. Yeah, and having this as a foundation, a common conceptualization, interoperable standards to structure data, we can also think about really building interoperable tools that connect different domains through a common exchange of information. This is now very much, if we take this common concept of a process and express the different aspects of processing in this pattern, we see, for example, if we want to transform materials, we are in the manufacturing domain. If we transform information, we are in the simulation and modeling world. And if we may also cross, we can also take measurements from material or control material processing with information. And if we take all resources into account, we of course assessing the sustainability aspects of such transformations, and could also be the sustainability aspect of data transformations of, for example, resource-intensive AI algorithms in the cloud. And yeah, here we see as researchers, it would be great to have this common knowledge graph of our work, establishing an inventory of the resources we need, so the materials, tooling, and resources, and we have also an inventory of processes we can apply or we develop to make our research happen, and collect maybe the data from machines, and then trigger workflows that support our work. That could be simulation, but it could also be exactly tools like openLCA that provide us additional insights in our work. And AI is, of course, a modern development that even makes this interaction more simple. Yeah, and this is pretty much based on my talk I give on the last openLCA conference. So it's really a little bit laggy, sorry. Yeah, the idea is now if we as material scientists create an inventory of materials and processes anyway, why not using exactly this inventory in a kind of a dual way? So on the one hand, of course, we can define all the substances we use and the properties, and we can define the processes and their parameterization, and then we create chains of processes to get our final material product. And what we conventionally do is we optimize the performance of the material. So this is what I did in my PhD, and this is where I stopped in my PhD. But having this inventory in place and having it represented as a digital asset, interoperable with other tools like openLCA, we can, with very limited extra effort, we can also make the sustainability optimization of the material. So having this dual perspective without recreating stuff. And this is then the vision to really connect this perspective of sustainability very early in our work. We already have this fundamental inventory of our materials and steps. Yeah, and what we developed as a prototype in the project is exactly this, that we have this inventory, we export the data in openLCA format. We have an expert running the an assessment, or it's a predefined assessment, and we get an insight, and we can feedback this insight to the material expert. Yeah, and I also brought here, so in detail, we then have this kind of ELN, or also electronic lab notebook and LIMS, lab inventory system, where you can input information, you get a graph representation of your workflow. We have this data transformation. We can export it, and we can use openLCA software as you know it. And here's also a live demo, or not live demo, but a video demo, how this works. Yeah, so this is the perspective of a material scientist. So he creates just his new planning of a lab experiment, of a synthesis, for example, and then he selects materials from his inventory. And so why not? So it's exactly the same material inventory as a LCA software needs to build up. And of course, because it's a process, it needs also quantitative flow. So we need to know how much of which substance is used for as input, and how much substance we expect as an output. Yeah, and we can also extend this to energy. So energy is, of course, typically not in the focus of a material scientist, but again, it's just a resource where we typically consume. For example, if you have an energy intensive drying procedure or heating, then we can maybe make not an exact value, but a rough estimation how much energy we need. And this data is, you can, of course, update the asset. You can change the procedure, or use it as a template and iteratively evolve it. But important is that what you do is not just another, let's say, custom format of this definition, but it's really a JSON file, which is also an RDF graph. So you can see how the different process steps are connected, and which flows feed into another. Yeah, so I cannot, so it's a little bit long, the video, maybe for the time we have. No, unfortunately cannot jump in another location. But yeah, at the end, we have an export interface that translates this to openLCA. So you can then pick a single process or multiple processes and export it. And our partner was then able to import this definition in openLCA. So yeah, it shows hand in hand, yeah, the work of an experimental scientist in an electronic lab notebook and LIMS system connected with openLCA. And the result was then stored back in our knowledge base. Okay, yeah. I think, yeah, okay. So this was how we can really connect tools because we rely on the same databases. And I want to finish the perspective that we also see common challenges in both domains. So if I got into touch with the sustainability community, I also heard that data availability is really a key issue. And this is also true for the material science domain as a whole. So we have a lot of publications, but we really lack of structured data. And we usually have just PDFs that explain something of an outcome, but it's not really accessible. And we are more and more into digital transformation, but also means that our tooling grows and grows and grows. And the cognitive challenge to use multiple tools to solve a complex task is also, yeah, leaving people behind that just refuses to make this change happen. And AI is it's not the all-in-one solution, but it's a promising solution. I guess also yesterday was some talks on this topic to support us in this challenge. The first one is, again, that AI can help us to access data. And with recent tooling, we can also provide a schema of our data and unstructured content. And the LLMs are then able to extract unstructured data and transform it to structured data. And this is a huge, I think, a huge benefit for all domains, especially material science, where we have more or less complex data information and very limited databases that, especially in the engineering of materials, where you usually have to take into account many aspects. So example is PFAS. So it's not that a PFAS substitute is a pure material, but it's often a material system that may is a multi-layered system or a composite material. And it may not work as a replacement under any conditions, because then it would be a perfect match and we already have a PFAS replacement, but maybe just under certain conditions, temperature-wise, regarding the atmosphere or humidity, however. So one idea is that, of course, to get all this publication data on material engineering and extract material profiles regarding the properties and the testing procedures and match this with machine readable requirement specifications. And AI can really support us in this, because by defining a schema that represents the information you need to extract, we can really speed up this process of data extraction. So on the one side, we see here a form which is rendered from the data schema, and instead of manually translating all this material and physical properties into the form, we can just upload a PDF and get it to an LLM, and it knows what we expect from him as an outcome. So this is really in a few seconds we have the data transferred. It's not 100% correct, of course, but maybe 90%, and we have the chance to make a validation and refinement. And most important, if we store this data, we really have a machine readable representation in a graph connected to a common taxonomy of materials, for example. So going from a PDF, which is really low data quality, to linked data in a few minutes is one improvement we get from AI already. And another approach is regarding tooling. So we have also here an example where we use a simple chat interface to explore the whole data and app platform we have here. So instead of searching the right entry point, we can let us guide through the LLM to the right concept or app in this platform. In this case, it's about uploading raw data set. And once we have the data set uploaded, it's of course accessible through the AI using something like tool calling. So large language models using APIs and programmatic functions. And then we can quickly jump to an interactive session with the LLM and the data. Yeah, you could phrase it like chat with your data. In this case, it's basically about evaluating a tensile test, so very common material science experiment, and generating a plot is then just a simple command which generates code, which loads the data and tries to fulfill the user's request. So it's really much quicker than a human would maybe take 1 or 2 hours to create a complex plot of his data, and now this is really in a few minutes done. And we can also store the procedure, how we process the data, how we create a visualization in an inventory, and redo it or reiterate our workflow. Yeah, and of course this also works with, I mean, this is also a very early prototype where we used description of material or material processing and use a schema that reassembles the lifecycle inventory. So we could read in the data, and we also use in the reverse process. So we try to validate the data set. It was extracted from proof documents by providing the same proof document or additional information to point the people to the right location where maybe there's some errors occur or something is maybe misaligned. So speeding up data generation, but also speeding up data validation is promising here. Okay, so finally, I want to close with, our vision is that really people are able within that domain to access tools that are not only reflect the core requirements of their domain, but also provide rich interconnectivity. That means if we as material scientists need a ELN, electronic lab notebook, lab inventory system, we should go the way that this system is really able to speak with other solutions and connect us with other domains like the sustainability domain. I think this will provide a foundation for sustainability by design in our domain, really have the knowledge and the feedback that our solutions are on a good way, or we can maybe rethink our decisions early in the innovation stage to where we still have an easy option to change something and not wait until we get a prototype and then maybe someone comes up with you shouldn't use this solvent or you shouldn't use this critical raw material in your product. Yeah, so I hope I could provide some insights, across domain insights, and I thank you very much for your attention, and if you still have time, I'm happy to take questions.
Thank you very much, Simon, for that great keynote. We have some time for some questions if someone wants to raise something already. I leave some space for people to take pictures of his contact details. Do we have one question already?
Thank you for this very nice talk. I'm Barbara Petschke from Austrian Center of Industrial Biotechnology. We are thinking about introducing electronic lab journals at the moment. Are there any advices or points where you say that one should consider to enable this connectivity? So are there only a few, as you showed, that fulfill this, or?
Yeah, I think the main issue nowadays is that we have millions of applications and they all have their internal data model. And if you need to connect one application, another, you also need to work on translating this internal data model. And this is really a challenge. And mostly we just give up on this and stay separated. So if you aim for this, I would pick a ELN which has the most open data model and a data model which is most already very near to your target application. So in this case, I would say it needs to be process centered and not material centered. Then it may becomes easier. I need to rethink if there's. I mean, there are a lot of options, and we also have our own system, so I'm a little bit biased on this. But we can talk maybe in the coffee break about more details.
Thank you very much, Simon. You mentioned SSBD on one slide, and I was looking forward to hear more about that, but you didn't elaborate. So maybe this is a future expansion, because especially in material science, you will come across materials that are not very well researched and that might have aspects regarding safety that don't come up in the sustainability part. You gave the example of PFAS, and PFAS is not really showing up in an LCA, but it is showing up in a safety assessment. Is this a future plan to extend the framework even more and taking in also aspects of persistency and bioaccumulation toxicity as an additional layer in the model? Thank you.
Yeah, that's a good point. So I think the ideal solution is that a material scientist is focused on his work, but if he designs a new synthesis and he points to materials, other people working on safety or on sustainability should use the exact same identifier, and this would allow us. So you point to a material here, and then you have a connection to another application or another community which uses this application, for example, to assess safety. And then so you send your material identifier, and then you get a safety or sustainability assessment here, and you transfer back the result, and then you get here maybe green or yellow or red light as a feedback. Yeah. So definitely we need to achieve an ecosystem of applications. Every application is focused on an aspect of SSBD driven by different communities, but we also need this data exchange happen to really provide fast feedback loops.
Nice. Maybe a question for myself as I wrap up this. Is this solution that's already mature enough to be, for example, bought by a company, or are you offering consultancy services with this? Or, you know, how usable is it by external people, this system? Is it internal to Fraunhofer?
Yeah, so in general, okay, I did mention this. In general, everything what we do is open source. Means you can find that the data models, the tooling for form generation, API generation, it's all on GitHub. And the platform openSymantec Lab itself as well. So we use it internally in 15 projects as a research data management platform, as a ELN, as a LIMS system. It's also available in the Fraunhofer Society as a web service. And you can host your own instance, of course, but it's a research product. That means I would say it's a beta product. And so we are not a commercial entity. So we are more into consultancy on this than providing a product. But maybe we go this way in the future. Let's see.